What's up guys, it's Simon Fios. Today's video is on AQAS of Chemistry, May 2023, Paper 2. Question 1, state what was observed in each case. So, I've got an aldehyde, I've got an alcohol, so I'm going to use Tollens reagent. The observation with the aldehyde, silver mirror. Observation with the alcohol, no visible change. Actually, the ketone, no visible change, not alcohol. Cyclohexane and cyclohexene, I'm using bromine water. Observation with cyclohexane, no visible change. Whereas cyclohexene, since it's got that carbon-carbon double bond, it's going to become colorless, or it decolorizes. Question 1.3, use the data to find out the relative atomic masses of hydrogen and carbon. Okay, so to find out hydrogen, I'm going to do C5H12 minus C5H10 to get 2 hydrogens equals, or in this case then, 72.1416 minus 70.1260, 2.0156, hydrogen equals 1.0078, 4 decimal places. Then to find the relative atomic mass of carbon, I know hydrogen, so I can find out carbon by just substituting hydrogen. So for example, C5H10, 70.1260 equals 1.0078 hydrogen times by 10 plus 5 carbons, we'll just say 5y. Therefore 5 carbons equals should be 7-8. Doesn't look like a 2-8. .0096. And then the final part says calculate MR of C6H6. When I'm just substitute that in, I'll just do 12.0096 times by 6 plus 1.0076 times by 6. So my answer times by 6 plus 1.0078 times by 6. 78.10444. 1.078, 12.096, 78.1044. Again, showing you how they can ask these kind of relative atomic masses questions in unfamiliar context. Question 2.1, state the meaning of the term fraction in this context. So, fraction is a mixture of compounds / substances with similar boiling points. So we'll just say mixture of compounds with similar boiling points. Identify the catalyst used. Well, it tells me it's catalytic cracking, so it's going to be a zeolite catalyst, or aluminosilicate, but yeah, zeolite catalyst, fine. Draw a skeletal formula of the alkane 3-ethyl 4-methyl hexane. So hexane firstly. 1, 2, 3, 4, 5, 6. We've got 3-ethyl and then a 4-methyl. That shouldn't be there. Let me draw it again then. So 1, 2, 1, 2, 3, 4, 5, 6. Perfect. 3-ethyl. So we've got 2 straight lines on the third carbon. 4-methyl, I've got 1 straight line on the fourth carbon. Perfect. That is 3-ethyl 4-methyl hexane in its skeletal formula. Good equation for the complete combustion of 3-ethyl 4-methyl hexane using molecular formula in your equation. So first things first, I need to find out the molecular formula of 3-ethyl 4-methyl hexane, which it doesn't tell me. But ethyl group, right? CH2, CH3, and methyl group CH3, and then hexane C6H12. And you add them all up, you get C9, C6, 7, 8, 9, H20. Perfect. Now the rest of it's easy. Complete combustion, so I'm adding oxygen. Enough oxygen to ensure products are purely carbon dioxide and water. Got 9 carbons on the left hand side, so I need a 9 here. But I've also got 20 hydrogens on the left hand side, so I need a 10 here. Then I've got 28 oxygen, so I need a 14 here. And that should be a bit more clearer. That's a 10 H2. Give one reason why carbon dioxide absorbs infrared radiation. You need to be very specific. You can't just say bonds are polar. What kind of bonds are polar? The C double bond O bonds, carbonyl bonds are polar. Carbonyl group bonds are polar. Same one environment that nitrogen monoxide causes. Acid rain. And what is used to remove it from the exhaust gases in petrol fuel cars? Catalytic converters. So it was meant by the term carbon neutral. There's no net emissions of carbon dioxide to the atmosphere. No net emissions of carbon dioxide to what? To the atmosphere. And the mechanism for nucleophilic substitution of 1 brom of butane with sodium hydroxide. Methane, ethane, propane, butane. Yep. Nucleophilic substitution, so I'm going to form an alcohol. And what happens is the lone pair of electrons on OH minus carbon's partially positive, that's partially negative, that's partially positive carbon, CBr bond breaks, and that's what you need to show. You don't need to show the product, but the product would just be the butane as it is, but you just replace the Br with the OH group, so then butane 1 on. State how figure 1 shows that rate of reaction rate 1 yield of butane is faster than state why the rates are different. So what you're going to need to use for this is the idea of the CF, CCl, CBr, CI, and you should know that faster. substitution as you go down, so aka faster rate, reason being lower bond density. So the first part state how figure 1 shows the rate of reaction of 1 iota butane is faster. You just talk about the gradient. Oh, sorry, the gradient is steeper. The gradient of iodide ions is greater. State why the rates are different. Well, you can see the Ci bond is lower in bond density than CBr, so that's what you need to say. Ci bond has a lower bond density than CBr, hence faster substitution. But you don't need to say any of that actually, you just need to say that because it's only 2 marks. 1 mark for your first part state, and it only says state, it doesn't say explain. So I'll just show you that Ci bond has a low bond density than CBr. Name and outline the mechanism for the formation of this major product. And I know it reacts with a hydrogen halide to form 2 structured isomers. Alkenes undergo electrophilic addition with hydrogen halides to form. So yeah, it's going to be electrophilic addition. Electrophilic addition. And it tells me this reacts with HBr to form 2 structured isomers. Major product is that. Name outline mechanism for the major product. Okay, so I've got 1-methyl cyclohexene, and I've got HBr, hydrogen halide, so hydrogen partially positive, Br partially negative. Probably should have done it up there, but I guess it's fine. What happens is the curly arrow from where? From the double bond goes to the H and then here. And I know I'm going to form 1 bromo, 1-methyl cyclohexane. So then I draw out the rest of it. Double bond's obviously gone now. Right, I've still got the methyl group, that's perfectly fine. But instead of that, so this stays the same. Obviously it's a hexane now because we lost the double carbon double bond. But instead of I've got a 1 bromo here, so then I've got a carbocation positively charged here, and then the Br minus with a lone pair of electrons goes to here. Right, and then it's going to bond to form 1 bromo, 1-methyl cyclohexane for 5 marks. Draw a to form the minor product form reaction, question 4.1. Well, the minor product, well, that's the major product because attached to looks like 3 alkyl group. The minor product is when the carbocation is here instead, because that's the only way you can do it. Yeah, you can't really have the carbocation here because that's not where the double bond was, so it can only be here or here. Yeah, so then if the carbocation is here, Br with a lone pair electron, Br minus will bond there, so you'll have this. You still have the methyl group there, but you have your bromo group here instead. And they always like to ask these questions. Then the next part of the question, explain why products are formed in different amounts. And it's always the same key points. 1-bromo, 1-methyl cyclohexane is formed via more stable carbocation. Major product from tertiary carbocation, like I said before, tertiary carbocation rather than secondary carbocation, and therefore stability from greater positive inductive effect or more electron releasing alkyl groups. It's always the same. You need to just compare it. Formed by more stable carbocation. On the left, major products formed from what kind of carbocation, rather than the minor products formed from what kind of carbocation. And then talk about stability from greater positive inductive effect or more electron releasing alkyl groups. To instruction, major product reactions of hydrogen bromide reacts with limonene or limonene. So this is limonene. When an excess of hydrogen bromide reacts with this, so what's going to happen is, right, here's where the double bonds are. In this case, it's got 2 double bonds, right? And it's asking for the major product, and that's really important because, let me get rid of this. Obviously, I'm going to have my Br either side of carbon double bond, right? But because I want the major product, I'm not going to have it here because that's going to be secondary carbocation. I'm going to have it here because that will be then, yeah, tertiary carbocation. And then in this case, limonene, if I have it here, the Br here, then that's just going to be primary carbocation. That's not what I want. And I can't have it here. I can only have it here, right? Yeah, and that will be tertiary carbocation. So that's what it's going to look like. So I've got this, a Br here. A Br here. Students provide with this much more sample of alcohol. Calculate enthalpy of combustion for the alcohol. Classic question, and always like to ask this type of question. Once you practice enough, it's really easy. So first thing I'm going to do is Q equals MC delta T. Well, it's not easy, but you know exactly what to do then. Where M is the mass of water. In grams. And I know I've got 0.250 kilograms of water, so it's going to be 250 grams. Times by C, which is 4.18, given in the question. Times by temperature change, which is just 78.1 minus 18.9. Then the moles, which is just the mass. Well, the mass of what? It's the mass over the mR. The mass of alcohol. The alcohol, which is, well, I've already, actually no, I don't even need to do that because it tells me moles of the alcohol. So that's perfectly fine. 0.0300. So moles 0.0300. Then to find out delta H and be combustion, it's Q divided by number of moles. But because I want delta H in kilojoules mole to power minus 1, I'm going to divide Q by 1000. So first find out Q. 250 times by 4.18 times by 78.1 minus 18.9 divided by 1000, and then keep my answer divided by 0.0300, and I get 2062. But because I know temperature is increased, I need a negative. Exothermic as temperature increases. Question 5.2, explain how you answer question 5.1. Suggests that the alcohol is B21O. Well, first thing you'll be saying these type of questions is heat loss. It is not accurate due to heat loss. Or you could say incomplete combustion, but heat loss is more preferable. And then the idea that the result from the experiment must be less exothermic than the true value. And what's less exothermic than the true value? Hence cannot be propan 1O or ethanol, because it's got to be less exothermic, it's just got to be more negative volume. And that's why. Question 5.3, use data to calculate why immune bond entropy depend on 1O. So energy required to break bonds minus energy released when new bonds formed, and I've got delta H minus 3388. Energy required to break bonds, so I've got I will draw this part out. So CH3, CH2 times by 3, CH2 OH. So energy required to break bonds. So I've got CH bonds. How many of them have I got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's going to be 11 times by 412 plus common carbon bonds 1, 2, 3, 4, 4 times by, well, that's what I'm trying to find, sorry. So 4y plus your carbon oxygen bonds 360 plus oxygen hydrogen bonds 463 plus your 7.5 O2. So O2 is just going to be 7.5 times by 496 minus energy released when new bonds formed 5 CO2. So we've got C double bond O, C double bond O, so 805. Basically, it's going to be C double bond O 805 times by 10. 6H2O, so 463 times by 12. the collect like terms. I'm going to be left with minus 3388 equals 9075 plus 4y minus 13606. I get 285.75. And it's obviously going to be positive in this case. And as I calculate energy density Buson 10, I'm given the density, I'm given the MR, so I'm given the density, so I'm guessing they're giving me the volume. Well, the mass is just going to be then the 810, because the density is usually 1 gram per dm cube. That's the mass of it. But in this case, it's in kilograms, so it's going to be 810 grams is the mass. So moles is going to be 810 divided by the MR. And then to find out the energy from energy density Buton 10, so I'm going to do my number of moles times by enthalpy of combustion of Buton 10. I don't care about the negative symbol, that just tells me it's exothermic. But that doesn't mean my answer is going to be negative. No. So times by 2676. 2929300. I remember it is positive. Question 6, state whether Cl bonds in dichloromethane and tetrachloromethane are polar. Carbon and chlorine have different electronegativities. State why tetrachloromethane molecules are non-polar. Idea that the dipoles non-polar, so dipoles cancel out due to symmetry. Then my tetrachloromethane has high boiling point than dichloromethane, but it's big. Well, the van der Waals forces between molecules, tetrachloromethane is CCl4, stronger than the van der Waals forces and dipole forces between molecules in dichloromethane, as CCl4 has more electrons than dichloromethane. So van der Waals forces between molecules in tetrachloromethane is stronger. The van der Waals force and dipole forces between molecules in dichloromethane because more electrons. Describe bonding, hydrogen bonding in propane mono. Attraction between oxygen, lone pair, and delta positive hydrogen of OH on another molecule. So the water should enter the condenser at the bottom and at the top. Ensuring condenser fills with water, as condenser is cooler, hence ensuring more vapor condenses. So ensuring condenser fills with water, as condenser is cooler. Name a complete mechanism of this reaction is going to be elimination. The mechanism, well, it's actually pretty complicated, this one, compared to the rest, like nucleophilic substitution, electrophilic addition, elimination. But this one's not your normal elimination. This one's a different one. Elimination of water from alcohols to form an alkene. So what happens is you've got your CH3, CH2, oxygen now bonds to that. So now what happens is it's got here, and now it's positively charged. And now what happens is go from here to here. Then you got your CH3, full marks for this as well, by the way. And all you have to do is just memorize this mechanism. Then this is carbocation positive charge, right? And you got your H2O plus your H2O. Then you and you want to form a double bond. So how do you do it? Well, it's gonna happen either way, but yeah, like that. Actually, no. So that first part happens. And you got your CH2 positive, but you ain't gonna form it like this or that, because that's carbon bonded to. It's gonna have to happen like that, and you can't do it that because that's attached to methyl group. So then it forms a double bond here. And then your final product might as well go through it. CH3, C, CH3, CH3, C, double bond, C, H, H, CH3, plus H2O, plus CH plus. Carbocation loses a H plus ion. Question 7.3 in similar experiment, this much produces this much butanol. You calculate percentage yield. So first things first, you calculate the mass. Density equals mass of volume. Therefore, mass equals density times by volume, which is equal to 0.818 times by 12. 9.816 grams. Once I've got the grams of what 233-trimethylbutanol, I can find out the moles of it by doing mass over MR. Then once I've got the moles of it, then I can use 1-to-1 mole ratio. Therefore, 233-trimethylbutanol, the same number of moles of that. Therefore, I can work out the mass of that. Moles in mass of MR, mass is going to be the moles, which I've got. times by the MR of 233-trimethyl butene. And the MR is going to be 98. So times it by 98, and that's the actual yield. No, this is a theoretical yield. Sorry, that's the actual yield. So now I do 6.12 over my answer times by 100, 73.8%. Question 8. Draw the Maxwell-Boltzmann distribution curve for fixed masses of gas at two different temperatures, 6 marks, and then explain where rate decomposition increases at high temperatures. So I've got this question is a perfect example why you need to memorize the Maxwell-Boltzmann distribution curve. You need to know every single part of it, because it could test you on any of it. So energy, then your number of molecules, number of particles, whatever. Then you've got your normal shape, obviously not a great sketch, but you get the point. Just copy and pasting the Maxwell-Boltzmann curve for your normal one, and then one at a high temperature, and then that's it. And then the final part, why rate of decomposition in grass increases at high temperatures, the idea that, and it gives you a lot of space. Maybe you're supposed meant to draw it on there, but increase at high temperature, molecules have more energy, more molecules have the activation energy, higher proportion of successful collision. So first point, very simple, molecules have more energy if you increase temperature, high temperature. More molecules have the activation energy, high proportion of successful collision. That's the end of section A.